Welcome to this video, where we'll explore an example of how metadata standards can support the process of aggregating microdata to produce statistical indicators. The first standard we use is DDI, a key framework for documenting microdata and describing survey processes. The second one is SDMX, the leading standard for representing and exchanging statistical data and metadata in the sector of official statistics. While both of these standards have extensive capabilities, we'll focus on their most common use cases using DDI codebook for microdata documentation and SDMX for representing aggregated statistics and associated metadata. To set the stage, let's have a look at the generic statistical business process model, or GSBPM in short, to outline the scope of the exercise. This demo will focus on the calculate aggregates suite process. We'll start with finalized microdata files, documented using DDI, perform data aggregation, and publish the resulting indicators using SDMX. To guide this transformation, we need a specification of the expected outputs, including details on how the aggregations should be performed. For this, we'll also leverage SDMX to express the required parameters in a standard way. To demonstrate the approach, we'll reproduce some official statistical tables published in survey reports. This will allow to test a metadata-driven approach with realistic use cases and validate both the data and the table layouts against a clear benchmark. We'll use two surveys for the demonstration. The first one is the Global School-Based Student Health Survey, or GSHS, conducted by the WHO. This survey collects data on young people's health behaviors and predictive factors. The second one is the Multiple Indicator Cluster Survey, or MICS, which is a household survey program developed by UNICEF and implemented in many countries worldwide. Here we see extracts from a GSHS fact sheet and an official MICS report, both originally published in PDF formats. The microdata for these surveys is publicly accessible online. GSHS data can be found on the WHO NCD microdata repository, and MICS data is available, for instance, on the World Bank microdata library. These repositories provide more than just microdata files. They include questionnaires, final reports, and documentation in various formats, including DDI codebooks. Microdata sets for GSHS and MICS are available under specific licenses, making them suitable for our demonstration. Indicators selected from the official reports will be reproduced as SDMX datasets and published on the sandbox instance of the .stat suite dissemination platform. We'll then compare the original and recalculated tables to validate the approach. For the exercise, we'll work with 6 statistical tables. For GSHS, point estimates from the fact sheets will be recalculated for 3 survey rounds: Fiji 2016, Samoa 2017, and Vanuatu 2016. For MICS, 3 tables from the 2019 official report from Tonga will be reproduced, covering housing characteristics, household and personal assets, and wealth quintiles. To map the DDI and SDMX models effectively, it's essential to understand how both standards represent data and metadata across different levels of abstraction. The framework I'll use here is inspired by the 4-layer metadata architecture developed by the Object Management Group, which is known for supporting cross-industry standards such as UML. So at the first and most concrete level, we have so-called domain data, which represents actual real-world datasets. Above this, we find a domain model, which describes the structure of the domain data and defines how it is organized. One level of abstraction higher, a meta model defines the rules for creating domain models. It establishes the standards and constructs used to describe statistical data structures. Finally, there is a fourth and most abstract level where we have a meta model, which provides the framework for creating meta models. At this level, the language becomes so generic that it can describe itself, but this is beyond the scope of the discussion for today. So let's explore how DDI and SDMX align with these layers, starting with the representation of statistical data. In DDI, microdata typically remains in its native format, in our case as CSV files. This corresponds to the domain data level in our layering. A DDI codebook will typically include sections on variables and data file descriptions, which outline the structure and meaning of variables included in the microdata set. This acts as a domain model representing the organization of the microdata files. The language used to describe microdata structures in DDI codebooks is specified by the DDI codebook specification and formalized as an XML schema published by the DDI Alliance. This aligns with the meta-model level in our 4 layers framework. In SDMX, data is represented using specific syntaxes defined by the standard based on XML or CSV, for instance. These datasets correspond to the domain data layer. The structures of the datasets are described with SDMX data structure definitions, or DSDs. These DSDs provide a formal description of the structure and the meaning of the datasets. This corresponds to the domain model layer in our taxonomy. The rules for expressing structural metadata in the form of DSDs are embedded in the SDMX information model, which constitutes a core part of the specification and corresponds to a meta-model layer. Having examined how data and its structure are represented in DDI and SDMX across different abstraction layers, let's now turn to metadata. Specifically, the descriptive information about data, commonly referred to as descriptive or reference metadata. We'll see the situation is slightly different. In addition to describing the structure of microdata files, DDI codebooks may include extensive descriptive information about the context in which the data was produced. Within our 4-layer framework, this corresponds to domain data, or we could say domain metadata in this context. The vocabulary used to express this descriptive information is specified in the official DDI codebook schema. We can see in this case that the official DDI XML schema provides a domain model for expressing descriptive metadata. In SDMX, reference metadata is used to carry descriptive information about data. This information is organized into metadata sets for which the specification defines possible formats, similar to how it handles data. The structure of these metadata sets is defined by the user through metadata structure definitions, or MSDs. MSDs specify the concepts and structure that the reference metadata sets correspond to, listing them at the domain model layer in our framework. The language used to describe MSDs is defined by the SDMX information model in a manner analogous to the treatment of data. Consequently, the SDMX information model for metadata structures resides at the meta-model level, as it did in the case of statistical data. From this analysis, we can see that SDMX provides a symmetric approach to representing both data and metadata. Domain data or metadata is represented using formats defined by the specification and adheres to user-defined structures expressed in accordance with an overarching information model that is part of the specification. DDI takes a different approach. A DDI codebook instance can be viewed as both a domain model for the dataset it describes and as domain content for additional descriptive information. Following this, the DDI codebook schema serves as a meta model for data and as a domain model for descriptive metadata. This asymmetry between the two standards is a critical consideration when attempting to bridge them. Mapping will be conducted at 2 distinct levels, the meta model level for statistical data and the domain model level for descriptive metadata. And by establishing general mapping at these higher levels of abstraction, it becomes possible to automate the generation of specific mappings for data structures, data sets, and metadata sets across any domain. Let's now explore the application architecture used for the proof of concept setup. A Ubuntu instance will act as a file server, hosting files downloaded from Microdata repositories and storing copies of the results generated at various stages of the processes. The Fusion Metadata Registry will manage all SDMX artifacts required to drive the process. These include data structure definitions for both source and target data, structure mappings, and metadata structure definitions. A PostgreSQL database will store a copy of the source data used in the process, and more importantly, it will serve as the environment where transformation steps derived from DDI and SDMX metadata are implemented. A .StatSuite instance will function as the dissemination platform, publishing aggregated statistics and their accompanying metadata. To orchestrate these applications, a layer of basic persistent services has been developed in Python. These services support essential operations such as reading and writing to the file system, the SDMX registry, the processing database, and the dissemination platform. For completeness, NADA, the software powering the Microdata repositories referenced in the demo, is worth mentioning. While it plays a role in providing Microdata repositories on the web, its operation is outside the scope of this demonstration. To facilitate the required operations for metadata-driven processes, some sample metadata processing services for handling DDI and SDMX metadata have also been developed in Python. In line with the concept of a no-code configuration for statistical processes, KNIME has been employed as a workflow manager. A series of custom composite services combining persistence and metadata processing capabilities have been prepared and made accessible on the sandbox KNIME instance. These composite services are more specifically tailored to the use case and provide coarser-grained functionalities. To give a clearer idea, some of the custom services integrated in KNIME for the demo include reading CSV and DDI files, transforming DDI to SDMX for both structure and reference metadata, validating and loading data into the database, mapping and aggregating data within the database, and publishing data and metadata. We'll now look at how the 2016 fact sheet for the global school-based student health survey in Fiji can be reproduced in KNIME, starting from a blank workflow. The goal is to use a DDI documented microdata file to produce aggregated statistics in SDMX based on a real use case. The process will be broken down into the following steps, which will be presented in details separately. First, the CSV and DDI files will be read and transformed into SDMX. Next, the microdata will be loaded into the database. The data will then be mapped from the source structure to the target structure. After that, the data will be aggregated according to the target structure. The aggregated data will then be published. And finally, metadata describing the source data and the processing performed will be generated and published. For each step, I'll demonstrate how the process can be configured in the sample KNIME setup using custom extensions developed for the demo. And I'll also provide additional explanations on the underlying approach where relevant. Let's now see concretely how we can do this. We'll start from a blank workflow with the necessary nodes on the left side of the screen. First of all, let's get the necessary source material from the WHO NCD microdata library. Here we are on the page of the Global School-Based Student Health Survey 2016 for Fiji. We have a DDI codebook documenting the survey, which is an XML file we'll download and use in the process. On the Downloads tab, we see a series of resources, including the reports published for this survey. We'll focus on the fact sheet, which is a PDF document, and these are the statistical tables we'll aim to reproduce. Returning to the Microdata repository, will now retrieve the microdata set. After accepting the terms and conditions, we'll access the download page for the data files, which are available in multiple formats. In this case, we'll download the CSV file. Going back to the overview page, we now have what we need: a microdata set in CSV format, a DDI codebook documenting the microdata, and the PDF report to reproduce. Let's switch to KNIME and start building our process flow. The first node will read the CSV file with the microdata. We'll place the node on the workbench and give it a label. Next, we'll open the configuration dialog and specify the file location by going to the first input box for the source folder. We'll copy and paste the file location from the File Explorer. And similarly, we'll copy the name of the CSV file downloaded from the Microdata repository. With the parameters set, we'll close the configuration dialog by clicking OK. And we can then execute the node by clicking the small triangle next to it. The green circle indicates the step has been executed successfully, and a preview of the data read from the CSV file is displayed. When nodes are executed, they produce flow variables that can be used by downstream nodes. These variables include parameters or execution metrics. The flow variable tab at the bottom of the screen shows the available flow variables for a node. And next to it, we have the data preview. The next node will read the DDI codebook. We'll place it on the workbench and label it appropriately. We'll connect the variable port to reuse the parameters defined in the first node. In the configuration dialog, we'll specify the location and name of the DDI file. For the file location, we'll reuse the value defined in the read CSV node from a flow variable. For the file name, we'll copy-paste it from the File Explorer. Once done, we'll close the configuration dialog. We'll execute the node, and a green circle will confirm successful execution. Let's now add a node to convert the DDI codebook into an SDMX data structure definition for the microdata set. We'll connect the read DDI node to provide access to the DDI codebook. Opening the configuration dialog, start by specifying the data file identifier. This is typically the name of the data file, so we'll use the CSV file name defined in the first step. And we'll also define the SDMX identifiers for the generated artifacts, including agency, version, and ID prefix. Save the output to the file system. We'll set the right output flag and specify the output folder location, copying it from the File Explorer. This will later be reused through the flow variable created by this node. With everything configured, we'll close the dialog and execute the node. In the File Explorer, we can now see an XML file created in the output folder. This corresponds to the SDMX DSD and its dependencies generated by the node. The DSD generated from the DDI codebook has also been loaded into Fusion metadata registry. And viewing the DSD details, we'll see that a row index has been added as a dimension. All variables have been translated into measures with data types or enumerations transferred as value lists. And each variable in the DDI codebook has a counterpart in the generated SDMX DSD. So for now, we have only one DSD describing the structure of our source microdata set. The next thing we can do is perform a structural validation of the microdata set against its DSD generated from the DDI codebook. For this, we'll add a validation node to the workflow. The DSD will be connected to the node. We'll also connect the CSV file. Running the validation, we'll call the FMR's validation service. A green circle confirms that the file is structurally valid. This means we have validated a CSV microdata set against its DDI codebook using an SDMX validation service. Now let's dive in a bit more details into how a DDI codebook schema can be mapped to the SDMX information model to generate an SDMX data structure definition. The starting point is a DDI codebook in version 2.5, which is mapped to an SDMX 3.0 DSD. A DDI codebook contains detailed information about the structure of the microdata set, as well as descriptive metadata related to the survey process, for instance. For this mapping, the file description and data description sections of the DDI codebook are used, as this describes the dataset structure. With SDMX version 3, this translation becomes more straightforward thanks to the new features designed to support microdata modeling, in particular, multiple measures and value lists. In practical terms, a row index is added as the sole dimension. All variables are represented as measures, and any possible categories used for variable values are modeled using value lists in SDMX. Now, let's focus on the mapping of elements between the two models. From the DDI file description, data structure definition, and a corresponding concept schema generated. For each variable in the dataset, a measure and its associated concept are created. Key elements of the variable are mapped as follows. The variable ID, name, and question literal in DDI are mapped to the concept ID, name, and description in SDMX, respectively. For variables with an enumerated value domain, a value list is created in SDMX. Each category within the DDI domain is represented by a value item in SDMX, with the DDI category value and label mapped to the SDMX value item ID and name. Finally, if a data type is associated with a variable describing a specific value domain, this information is transferred to the SDMX DSD with the local representation of the corresponding measure. By following this process, we achieve a comprehensive mapping that translates a DDI codebook into an SDMX data structure definition. As the next step, we load the microdata into the database where the processing will take place. Let's add a generate table node to the workflow and give it an appropriate label. We'll connect the SDMX DSD that holds the structure of the dataset, and we'll also connect the dataset containing the data to be uploaded to the database. Both the structure and the data are returned by the validation node. We'll now to configure the node. First, we provide some information about the name of the table in the database. A table name prefix is required, and we'll reuse the SDMX identifier prefix specified earlier. We'll also keep the default table level identifier that is proposed. We'll set the right output flag so that a copy of the outputs produced by the node is stored on the file system. It's useful for tracking what happens during the process. We can now close the configuration dialog by clicking on the OK button and execute the node. After execution, we can go to the File Explorer and check the output folder. We'll see that two files have been added, an SQL file containing an SQL create table statement generated from the SDMX DSD, and a CSV file with the data that has been uploaded to the database. We can go to pgadmin to see what the results look like in the database. We can see that a table named GSHS T1 source has been created, and opening it will confirm that the microdata has been successfully loaded into the database. I'll now provide some more details about the step of creating a database table from an SDMX dataset with its accompanying DSD. PostgreSQL is used as the processing engine in subsequent steps. Loading the source microdata as a database table is the first step in the processing chain to be implemented in the database. Materialized views will later be generated from SDMX artifacts to perform data mapping and aggregation, building on the microdata table we just loaded into the database. An SQL create table statement is generated from the SDMX DSD. Future components are transformed into columns in the database with data types derived from the DSD were specified. For coded components, a text data type is used. The CSV microdata is then loaded into the created table. Each variable in the microdata file corresponds to a measure in SDMX and a column in the database table. Values for the row index, which serves as the unique dimension of the dataset, and the first column in the database table are inserted in the CSV file in the initial file reading step. Let's now proceed with the mapping of source microdata to the target structure. The source data structure has been generated from the DDI codebook. To continue the process, we need a specification of the target data structure and the mapping between the source and target structures. The target data structure will be represented using an SDMX 2.1 compliant DSD. The mapping between the source and target DSDs will be represented using an SDMX 3.0 structure map. These elements have been created using the FMR and will be reloaded without going into the full details of their preparation. I'll provide some more information on how the target data structure and the structure map are composed a bit later. So switching back to the Fusion Metadata Registry. We start from the welcome page. We can load new structures into the registry by selecting a file to upload. I'll select a file prepared specifically for this demo from the file system. Once the file is selected, we can initiate the import process. A summary of the SDMX artifacts contained in the file will first be displayed. After confirming the import, these elements will be loaded into the registry. The import is now complete. If we navigate to the data structure section, we'll see a new structure has been added. Viewing the details of this structure, we will notice it includes several dimensions: area, age, sex, and indicator. Each dimension is associated with a code list. For example, the indicator dimension has a list of 39 possible values. Let's close this detailed view of the target data structure definition. Next, we'll examine the annotations associated with the DSD. We can see specific aggregation annotations linked to the indicator dimension. These specify how different indicators should be aggregated. For instance, the average age is aggregated using a mean function rounded to 2 decimal places and weighted using a column called weight in the source microdata set. Let's now look at the structure map linking the source microdata structure generated from the DDI codebook to the target data structure we just loaded. Viewing the details, we can see mappings between the source and target structure components with specified mapping rules. These rules include fixed values, identity mappings, or representation maps. In some cases, multiple source variables are mapped to the same target components. This involves reshaping the data from white to tall in line with the SDMX 2.1 monomeasure approach, where indicators are distinguished by the indicator dimension. Let's take a closer look at a specific representation map. Viewing the details, we can see how values from the source DSD value list map to target codes in the code lists of the target DSD. So now, in addition to the source DSD generated from the DDI codebook, we have a target DSD and a structure map linking them. Switching back to KNIME, we'll add a node to our workflow to apply the mapping to the microdata loaded into the database earlier. Connect the SQL generated by the generate table node, which retrieves the name of the source table in the database. Next, we'll add a node to retrieve the structure map from the Fusion Metadata Registry and make it available for the process. This node will be connected to the node performing the mapping. We'll need to configure this node. First, specify that we want to retrieve a structure map from the registry. Then indicate the agency ID and version of the structure map. The configuration is now complete, and we can proceed to execute the node. Moving back to the apply mapping node, we need to configure it as well. We use the same table name prefix and keep the default table level identifier. Next, we'll set the parameters for writing the output to the file system. With the configuration ready, we can close the dialog and run the node. In our output folder, we see two new files. A SQL file containing an SQL create materialized view statement that implements the structure mapping, and a CSV file containing a download of the data mapped by the materialized view in the database. Finally, let's check pgadmin to view the results in the database. We can see a newly created materialized view, and opening the table, we'll find a mapped version of our dataset. Let's take a closer look at how the mapping step works. The starting point is the source data structure definition, which replicates the DDI codebook describing the microdata file. This is an SDMX 3.0 DSD, where a row index serves as the unique dimension and all variables are represented as measures. Categories are defined through value lists. A target DSD has been defined as an SDMX 2.1 DSD. This structure has a single measure and uses an indicator dimension to distinguish between different indicators. In this case, categories are represented with code lists, and the dimensionality of the data cube is defined by the set of dimensions and the hierarchies of the code lists. Specific annotations are included to indicate aggregation details, such as the aggregation function, rounding, and weighting. The transformation of a codebook into an SDMX DSD is based on a fixed mapping at the meta model level, allowing to transform a codebook into a DSD for any dataset. The mapping from source to target structure operates at the domain model level and is specific to the process. To illustrate the mapping, let's consider an example. Suppose we have a source data structure with a row index and several variables corresponding to survey questions, along with a target structure comprising a series of dimensions and one measure. Different types of mappings can be applied. For some dimensions, a fixed value may be assigned if it remains constant across the dataset. In other cases, values may need to be recoded. This is achieved using an SDMX representation map. For instance, in the example, age and sex require recoding to different sets of codes in the source and target tables. Additionally, a default value can be specified for cases where no explicit match exists. Since source data structures are typically wide multi-measure structures and target structures are typically tall monomeasure structures with an indicator code list, it is often necessary to map one source measure to multiple components in the target structure. In this scenario, a source variable corresponds to a value in the target structure, but is further differentiated by a specific indicator code and a specific unit of measure. And because multiple variables from the source structure are integrated into the target structure, this mapping pattern is repeated multiple times, resulting in a many-to-many relationship between source and target structure components. So far, we have discussed data structures. Now let's see how this works in practice at the data level. Let's consider a single row from the source data set where two measures or variables need to be mapped. The first value in the sample source record will result in one row in the target table, but mapping the second value from the same source record will produce a new row in the target table. This process effectively transposes the data, converting a wide data set with variables as columns into a tall data set with indicators as rows. So to summarize, variables are represented as measures in the source data are mapped to dimensions, measures, or attributes in the target structure. Values can be fixed, transferred as is, or recoded. The mapping of source components to target components can be done one-to-one, one-to-many, or many-to-many. This may involve complexities in the mapping process, such as data reshaping. Specifically, mapping a multi-measure SDMX 3.0 structure to a mono-measure SDMX 2.1 structure involves a wide transformation. This transformation is implemented in a PostgreSQL as a materialized view generated from the SDMX 3.0 structure map. Once microdata is mapped to the target structure, the next step is aggregation. Let's add a node for aggregation and give it a proper label. We'll connect the SQL port from the node performing the mapping. This allows us to get the name of the materialized view from which data is to be aggregated. Similarly to what we have done in the preceding step, we'll add a node to retrieve the target DSD from the registry. We'll connect the SDMX port to the node performing the aggregation so that the target structure is available to it. We'll need to configure the node. To do this, we'll specify the type of objects and the identifiers of the SDMX artifact we want to retrieve. Once this is done, we can close the configuration dialog, then we'll execute the node. Let's go back to the aggregation node. We'll also need to configure it. First, we'll set the table name prefix, reusing the one set previously, and confirm the default table level identifiers. This time, we can see that there are 3 of them. We'll set the parameters for writing the output to the file system. Then we'll close the configuration dialog and execute the node. If we go to the File Explorer, we can see that a series of new files have been created by the aggregation node. For each of the steps, denormalization, aggregation, and filtering, there are 2 files. SQL file corresponding to the create materialized view statement, implementing the transformation, and 1 CSV file containing the data downloaded from the materialized view. If we switch now to pgadmin to see what has happened in the database, let's refresh the lists. We can see the flattened age table showing the different levels to which each individual age category is associated. In this case, there are 4 levels of detail for age. The same applies to the sex table, except that here we only have 2 levels, sex, categories, and total. Denormalization view merges the flattened code lists with the mapped data table as a preparation for the aggregation. And similarly, an aggregation view aggregates the denormalized data according to the dimensionality and levels defined in the DSD. And finally, a filtering view excludes some values, notably based on a defined SDMX content constraint. This results in a final table of aggregated statistical indicators. The aggregation is implemented in 3 sub-steps. In the denormalization step, flattened SDMX code lists are loaded as database tables. The content of these tables is calculated from SDMX code lists where parent-child relationships are present. Data is joined to these flattened code lists so that each row contains for each dimension the codes of all levels in addition to the lowest level originally present in the data. In the aggregation step, data is aggregated by combinations of levels using the SQL group by grouping sets clause. Levels are collapsed back to dimensions using the SQL coalesce function. In the filtering step, null values generated in the previous step are excluded, and values are excluded based on the SDMX content constraint. Different types of hierarchies need to be supported to aggregate statistical data. In the simple case, a flat list of categories does not require aggregation. A balanced hierarchy occurs when all child categories have parents at the same level. For example, a total may simply be added, creating 2 levels, but there can be more levels. Unbalanced hierarchies may be trickier to handle. An example of this is the age dimension in the dataset we're using. And another special case arises when several root nodes are present, which requires special handling. Let's walk through the steps using a single data record as an example. In this record, we have 5 dimensions, 1 measure and 1 attribute. The reference area is FJ, the sex is male, the age is 15, the indicator is average weight, the time period is 2016, the observation value is 1.65, and the unit of measure is meter. If we denormalize the sex dimension, we get at level 0 the original value, which is the most detailed level, M for male, and at level 1 we have underscore T for total. Similarly, if we denormalize the dimension age, we get at level 0 the original value, which is the most detailed level, 15. At level 1, the 13 to 15 grouping. At level 2, the 13 to 17 grouping. And at level 3, the total aggregating all age categories. Next, we execute the SQL statement using grouping sets for the levels of the hierarchical dimensions, sex and age. This produces a series of possible combinations with observation values aggregated using the defined aggregation functions. A series of null values is generated for sex and another for age. We select the first non-null values in the different sex levels considered in ascending order, and collapse this to the sex dimension using the SQL coalesce function. The same approach is applied to the age dimension to bring back relevant values to the age dimension. We then drop the level columns, keeping only the original set of structure components. At this point, a series of null values remains in the dimensions. These correspond to automatic totals, but will be discarded since totals are recalculated separately to handle cases with multiple root nodes in code lists. Filtering out these values results in the final table, where data is aggregated according to the dimensionality defined by the DSD. This is achieved through the dimension and the hierarchies of the associated code lists. So to recap on this, the cube dimensionality is defined by the dimensions from the target DSD and the levels in the associated code lists. Annotations in the DSD specify for each indicator the aggregation function to apply to unit level observations, the rounding rule, and any weighting variable to be used from the microdata set. SDMX content constraints specify filters to apply to the aggregated data. This allows excluding certain values, such as the lowest level aggregates, if they are not intended for publication. The aggregation and its 3 substeps are implemented as SQL materialized views. These views are generated from the annotated SDMX 2.1 DSD, defining the output table to be produced from the mapped microdata. Now that we have the data mapped and aggregated, it's time to publish it. We'll begin with the Data Lifecycle Manager, DLM, and upload the structures corresponding to the data flow we want to publish. First, we'll select the file containing the SDMX 2.1 artifacts to load into the .stat suite. Next, we open the file in the DLM, choose the appropriate data space where we want the content uploaded, and confirm the upload process. If we check the list of available data flows, we'll now see a new one for GSHS, which currently contains 0 observations. Let's switch back to KNIME. On the workbench, we'll place a published node and give it a meaningful label for clarity. Then we connect the aggregate node to the publish node, allowing it to access the aggregated dataset we want to publish. Now it's time to configure the publish node. Let's open its configuration dialog. We provide the reference for the data flow, where the data will be uploaded. As with most SDMX artifacts, this reference includes 3 parts: the agency, identifier, and version of the data flow. With that, the node is configured, and we can close the dialog by clicking OK and execute the node. A green circle will indicate that the task has been successfully completed. If we check our mailbox, we'll find a notification email from the .stat suite confirming that the data has been successfully loaded. So finally, let's go to the Data Explorer to view the aggregated dataset. After refreshing the application, we can access the data table. And here we'll see a series of values for the different indicators broken down by sex and age categories. Let's compare the results produced by our metadata-driven process with the official fact sheet. At the top, we can see a portion of the GSHS table from the official fact sheet, and below it, a screenshot of the Data Explorer. While we are only looking at a subset of figures here, each one has been verified and matches the official data. Additionally, the original layout of the table has been preserved, ensuring consistency in presentation. This successful alignment confirms that our process is validated. Now that the data has been published, let's see how we can enrich it with additional metadata about the source microdata using our DDI codebook. First, we'll create a node to convert DDI metadata into SDMX format and label it appropriately. Next, we'll create a node to retrieve the metadata structure definition from the registry. We'll connect the MSD. Then we'll connect the target data structure definition as well. And we'll also link the DDI codebook. Finally, we add a connection to import variables from the DDI to SDMX structure node. This step ensures we can retrieve the output folder location specified earlier. So returning to the retrieve MSD node, we'll open the configuration dialog, and here we'll see the reference to the MSD to be retrieved. After this, we'll close the dialog by clicking OK and execute the node. Next, we'll return to the DDI to SDMX node, configure it. We'll keep the default DDI namespace. In the DDI link field, we'll add a link to the source on the web. To get the link, we'll go back to the browser on the page of the Microdata repository where we downloaded data and metadata and copy-paste the URL. We can also specify a metadata target using key value pairs. For this example, we'll indicate that the metadata applies to Fiji for 2016. Lastly, we'll configure parameters for writing output files to the file system. Let's close the dialog by clicking OK, and with the configuration complete, we'll run the node. In the output folder, we'll find a new file, an SDMX metadata set generated from the DDI codebook. To publish this metadata set, we'll add and execute a publish node. Shortly after, we'll receive an email notification from the .stat suite confirming that the metadata set has been successfully loaded. Opening the Data Explorer, we'll refresh the table view. And now an eye icon will appear next to the table title, indicating the availability of reference metadata. Clicking on the icon opens a side panel displaying the metadata information. Scrolling through the panel, we can see a series of metadata attributes, all derived from fields in the DDI codebook. Additionally, the link to the source repository is included for reference. So here we have metadata from the DDI codebook published as an SDMX metadata set on .stat suite. This content is visible in the side panel that opens when clicking the metadata icons displayed in the data viewer of the Data Explorer. This relies on a DDI SDMX mapping. The DDI XML schema is mapped to a specific SDMX metadata structure definition. The actual DDI codebook is mapped to an SDMX reference metadata set with elements from the DDI codebook transferred to metadata attributes in the SDMX metadata set based on the model level mapping. The content covered here focuses on the descriptive sections of the DDI codebook, specifically the document description and study description sections. Other sections were used to generate the data structures. It consists of general level metadata documenting the source microdata used to produce the indicators. Let's look at a concrete example of how this is implemented for a specific attribute in a metadata set. Attributes of the metadata set to be published are defined in a metadata structure definition. These attributes are annotated with an XPath expression, which points to a specific element in the official XML schema that defines the DDI codebook structure. The value of the element in the DDI codebook is defined by the schema and as such is linked to it. The loop can then be closed by transferring the attribute value to the SDMX metadata set. This way, the mapping from the DDI codebook to the SDMX metadata is inferred from the mapping between the SDMX MSD and the DDI XML schema for all attributes. Finally, we'll see how we can add some more information about the processing of individual indicators and the mappings from source to target data. Let's add the node to the workbench to transform SDMX mapping to reference metadata associated with our indicators. We need to connect the structure map. We'll also add a connection to import flow variables from the DDI to SDMX node so we can retrieve some parameters defined previously. Let's open the configuration dialog. We'll reuse the metadata target previously defined. Let's then set the parameters for writing the output to the file system, also reusing previously defined parameters. So we are done with the configuration. Let's click OK. And now let's run this node. If we go to the File Explorer, we can see that we have another metadata set. Let's go back to KNIME. We'll add a last node to publish the new metadata set and execute it. As with all publication actions, we'll receive an email notification from the .stat suite confirming the successful upload of the content. Let's see what this looks like in the Data Explorer. If we refresh the data view, we'll see that each indicator now has its own little eye icon indicating the presence of reference metadata. If we click on one of these icons and open the metadata panel, we'll see some additional information such as the source variable, value mappings, aggregation function, rounding, and weighting applied. So here we have just added some additional metadata, providing specific information on the processing performed for each indicator calculated from the source microdata. This information is made available at the indicator level and can be seen in the Data Explorer in the side panel, in addition to the general level metadata transferred from the DDI codebook. Some metadata comes from the DDI codebook via the generated source DSD. This includes the source variable label, the source variable literal as it is called in DDI, and the source variable categories with their labels if available. Some more metadata comes from the SDMX structure map, specifically the mapping between variables in the source dataset and indicators in the target dataset, as well as the possible value mappings. Additional metadata is collected from the target SDMX DSD, including the aggregation function, rounding parameters, and any weighting used. Altogether, this provides detailed metadata that fully documents how microdata has been processed to produce the given indicator. We'll now consider different ways of going a step further with this metadata-driven approach. A first way we can take this approach further is by observing that the process developed is quite generic. As an example, this is the process flow we just prepared for GSHS, for Fiji, and for the year 2016. Now, this is the one for Samoa 2017. And this is the one to process data for Vanuatu 2016. What we see is that the process flow is the same. What differs from one case to the other is the data and metadata fed to the process. Another way of going a step further with this type of process, now that we know the process flow remains the same for different surveys, is to loop over different countries or tables. Specific nodes can be added to the workflow to loop over different parameters defined in a CSV file, where each row is loaded as a set of flow variables used as parameters for the different executions of the process. Here we see what the parameter file looks like for our 3 executions of the GSHS process. Parameters differentiating the different execution cycles include the source folder, the source DDI and CSV file, the SDMX prefix to be used for the outputs generated, the structure mapping to be used, the metadata target, and the link to the source microdata repository included in the metadata. Executing the loop produces the table for Fiji, Samoa, and Vanuatu. While we won't do a detailed comparison here, all figures are accurately reproduced, and the layout of the tables is equivalent to the official fact sheets published. Another way to extend this approach is by generating the target SDMX structure and mapping from a spreadsheet instead of using the graphical user interface. This can be a more efficient option, especially when many indicators need to be produced for the same table. Here is a workflow for processing the MICS 2019 survey for Tonga to produce table 2.1 on housing characteristics. In the initial case, the target data structure definition and the structure map must be prepared manually using the graphical user interface of the Fusion metadata registry. This can be relatively cumbersome, particularly when specifying mappings from source variables to target indicators, which include the indicator code, the actual value, and the unit of measure for each indicator. This could instead be done using a spreadsheet template that includes all necessary information for mapping from source to target data. The target DSD and structure map could then be generated and loaded to the registry as part of the process execution. This method can make it more convenient and efficient to specify a large number of mappings. It also allows the process to run automatically from start to finish without requiring manual editing or loading of the SDMX resources as part of the workflow. Here is an example of what such a spreadsheet might look like. The first columns specify the target structure in terms of component roles and representations, followed by mappings to the source variables and the aggregation methods. This approach has been validated with the replication in the Data Explorer of Table 2.1 on housing characteristics from the MICS 2019 survey for Tonga, including both general level and indicator level metadata. So putting this all together now, here is a workflow looping over the 3 selected tables for MICS 2019 for Tonga, generating the target structure and mapping from a spreadsheet. The tables reproduced by this process are the table 2.1 on housing characteristics, table 2.2 on household and personal assets, and table 2.3 on wells quintiles. In this workflow, we use a loop where each process iteration generates SDMX target structure and mapping from a spreadsheet and applies it to a DDI documented CSV file. The parameters file used for the loop becomes very simple in this case. Here we see an overview of the SDMX data flows published on our sandbox.stat suite environment. We have one consolidated GSHS dataset with data from 3 countries and 3 data flows corresponding to the 3 mixed tables reproduced for 1 country. I won't go into the details of the comparison, but the 3 mixed tables for Tonga have been successfully reproduced using the presented workflow. All figures are accurate and the layout matches the tables included in the official publication. Now, some conclusions. DDI and SDMX can be used together to support microdata aggregation, leveraging the specific coverage and strengths of both standards. Expert work remains essential for designing statistical outputs and specifying how source data is mapped and aggregated. This approach enables a metadata-rich dissemination of statistical indicators, providing a complete description of the source microdata and how it is processed, while linking DDI microdata repositories to SDMX statistical dissemination platforms. The exercise furthermore revealed a generic microdata aggregation process where domain-specific business logic is fully embedded in DDI and SDMX metadata used by domain-independent software building blocks, following a metadata-driven approach. The process promotes the so-called standards-based industrialization of statistical production, supporting greater agility, faster time to market, improved repeatability, and enhanced efficiency in statistical production. Thanks for watching.